We are inside a hyperscale data center chiller plant. The cooling architecture here relies on the continuous interplay between massive air-cooled chillers, open cooling towers, and an expansive network of chemical treatment skids. In this environment, water treatment operates as a primary mechanical defense system. It is specifically engineered to prevent catastrophic plant failure. This Venn diagram maps the strict operational mandate: maintain clean heat transfer surfaces and discharge quality without compromising server cooling availability. This yields a foundational rule: treatment processes may be halted during a fault, but the critical cooling flow must remain active at all times. The strategy depends on the system type. In open recirculating loops, evaporative concentration and mineral scale are the primary risks. In sealed closed loops, the threat shifts to oxygen ingress and inhibitor depletion. To manage these risks, interfaces require rigid ownership. The mechanical boundary isolates supply and return fluid. Controls own the safeties and interlocks. The electrical interface governs normal and standby power, and the water interface proves the analytical chain of custody. Achieving the core mandate requires every physical, electrical, and chemical boundary to enforce one outcome: cooling flow overrides treatment. This illustrates the volumetric trade-off of evaporative cooling. Pushing a system from 5 cycles of concentration to a target of 10 COC drops required makeup water significantly. Moving to 10 COC cuts blowdown waste by 58%, drastically reducing overall water consumption. However, operating at 10 COC pushes the circulating water chemistry to its physical limit. Go any higher, and dissolved minerals will precipitate out of the water, forming solid rock directly onto the internal chiller tubes. This chart defines the limiting chemistry capacity ceiling. System efficiency is bounded by the least tolerant mineral in the source water. Here, calcium hardness is the limiting factor, restricting the entire system to a ceiling of 10 cycles of concentration, despite others having higher tolerances. If a facility attempts to push past these specific limits, active mitigation is required. Engineers must deploy skids using sacrificial magnesium oxide to artificially force down dissolved silica spikes before they scale the pipes. Maximizing cycles of concentration saves millions of gallons of water, but it eradicates the operational margin for error. It turns water chemistry from a passive monitoring metric into a volatile, immediate threat. This flowchart dictates safe chemical injection: authorize the product, calculate mass, isolate the feeder, and prove flow. Crucially, a physical sample must verify chemistry before restoring operations. This hold point prevents returning to automatic authority until the valve lineup is proven safe. Blind dosing bypasses the physical verification of product strength and system volume. If a high concentration of oxidizing biocide or an acidic cleaner hits the metallurgy without sufficient dilution, it will immediately spike the corrosion rate on copper and carbon steel surfaces. Chemical management controls the dissolved mineral envelope, but it cannot prevent the accumulation of physical solids. In an open tower, environmental dust enters the system and provides nucleation sites where dissolved minerals begin to crystallize. This side stream loop removes physical dust. Hydrocyclonic sweep nozzles push dirty basin water into a centrifugal separator, removing heavy solids, before high-performance filters capture sub-5 micron particles. This continuous kidney loop enables zero downtime cleaning, returning clean water without interrupting the main cooling tower. This cascading logic dictates side stream loop sizing. While a 20% design margin covers operational uncertainty, true redundancy requires 2 completely independent units, each rated for 100% flow. Warm water at 10 CoC breeds Legionella. To prevent fouling, dual-headed dosing skids instantly shift to a backup if pressure drops, eliminating biological dead time. During biocide injection, a safety interlock seals the blowdown valve for 4 hours, preventing toxic flushes into municipal systems. Without redundant mechanical filtration and automated pathogen lockouts, the delicate chemical balance of a high CoC environment will collapse, leading to biological fouling and severe scaling. The physical benchmark of this entire water treatment architecture is thermal efficacy, maintaining a 0 fouling factor on the heat transfer surfaces inside the chillers. Chemicals alone will eventually fail to maintain this perfection. To preserve the approach temperatures, continuous physical scrubbing of the condenser tubes is required. This cycle relies on an interference fit. Vulcanized rubber sponge balls are injected into the supply flow, wiping each internal tube wall to remove soft scale before it cures. Downstream, a vortex screen catches the returning balls for recirculation without impeding the bulk cooling flow. The engineering tolerances here are extremely tight. The ball material, exact diameter, and compression hardness must be perfectly matched to the localized water chemistry and the specific metallurgy of the condenser tubes. This continuous mechanical scrubbing serves as a final mechanical shield. It protects the data center's power usage effectiveness from the steep performance degradation that high COC scaling would otherwise cause. Monitoring this volatile system requires central instrumentation. The core rule of telemetry is sample validity, representative, conditioned, and actively flowing. Stagnant water renders automation useless. This flowing sample enables real-time corrosion tracking, allowing operators to adjust inhibitors before pitting occurs in copper and carbon steel. Centralized instrumentation creates vulnerability. This diagram explores blast radius architecture, demonstrating how redundant systems fall victim to common mode failures. In Scenario 1, a single blocked sample header causes all sensors to read dead water, crashing both dosing pumps and blowdown valves, causing total treatment loss. True system redundancy requires physical separation. Measurement lines, control power, and discharge paths must be isolated to prevent a single controller failure from blinding the entire plant. When failures occur, operators rely on this FMEA matrix to categorize risks and responses by priority. A Priority 1 chemical spill demands immediate emergency response and pump isolation. Contrast that with a Priority 2 filter pressure warning, requiring a deliberate manual backwash investigation. When water chemistry falls out of the approved envelope, engineers execute this diagnostic flowchart to find the root cause. Step 1 is unbreakable. Protect the cooling flow first and stop unsafe dosing second. The data center's thermal load is always the priority. Operators use this 4-quadrant performance dashboard as the single decision layer to converge telemetry. Notice the correlation. A physical change in mechanical health, like a spiking filter pressure curve, will mathematically impact thermal efficacy, driving up condenser approach temperatures over time. No single metric provides a complete picture of plant health. Operating a high COC plant safely requires correlating chemistry, mechanical water use, and thermal efficiency to identify physical root causes and prove the system has recovered before restoring automatic authority.